Hello, everyone. Welcome to our workshop. Thanks for your patience. Today, we'll talk about deep learning. Our speaker, Humayun Irshad, will be with us. He's a data scientist at Synthesis AI, and he's also instructor at Magnimind Academy. Before we start, I want to talk about our company, Magnimind Academy. We founded in 2015, and we've been teaching data science since 2015. We have different programs, including machine learning, deep learning, natural language processing, and some beginner level courses like Introduction to Python, Python for data analysis, SQL. Right now, we have our mini bootcamps, which we are accepting applications. One of those mini bootcamps is our deep learning mini bootcamp, which will be given by Humayun Irshad. I assume he will mention in detail later. With that being said, I want to announce Humayun Irshad with a round of applause. Thank you.
Thank you. Okay. So I will start first the background about you. So how much you know about deep learning? Do you ever write a single program in machine learning or deep learning? In Python or C++? And which framework? Tensorflow, Keras, Tensorflow, PyTorch. Okay, so the format of this today workshop is, so I will give you at the basic how deep learning work, how machine learning work. So most focus on deep learning, not machine learning. So how one single neuron work, and then how you combine a bunch of neurons in different layers so that it can start learning things, and how we can make a system that can understand digit, any type of images. And because this is 2-hour session, so we will more focus how one neuron at the lowest level is working. So how we can train neuron, how neurons learning stuff, and how we can use that learning to make a system that can classify image. Okay, so I would like, if you have computer, you can download this code and you can run in the meanwhile I'm telling you. So I will run all my code here. Okay, so you can understand how things are working. So for the code is at GitHub. So you can go on my profile, github.com/Humayun/machine_ML_workshop and download this whole material. So they had presentation, instructions to install packages, and all the code. So I mostly use the Anaconda environment. So Anaconda is kind of like package where you can install and different packages. I can create different environment, and one environment for one project which has similar packages, and then you can create as many environment as you want. And you can later, if you want to change your system, just and save the environment, and then you can take that environment to another machine. It can be with different computers, one on Linux, other one on Ubuntu, Mac, or Windows. So same environment work on all different platforms. Okay, so let's start with the slides. So one single neuron we call perceptron. So I start with that, how perceptron work. So starting from example, so we have two variables, and taking example of a student. One is a test score, second is grade, and based on these two, we will decide either the student pass, accept, or reject for a interview or for a test. So whenever in machine learning, so we have two variables. One is dependent variables, and second is independent variables. So these two are independent variables, which we have like test score or grades, and the dependent variable is the outcome of these two, which is the prediction. So what we are predicting, either the student accept or reject. So on what we do, so we plot, we have data set of like more than 100 students which have scores and grades. So we just plot here on x-axis we have tests scores. On y-axis, we have a grade score. So each dot represent one student value. And then, so if you want to predict a student which have 4 score in the test and 8 in the grades, what is chances of the acceptance or rejection of that student? So this is the student dot here. So what we need to do, so by looking at the data, so we have 2 colors, red and blue one. So we already had some labels that these students, the blue one are accepted and red one are rejected. So we can assume that based on this location, so this is more like locality is on rejection, so this student will reject. But in real machine learning, how we can come up with this one? So the machine learning, it need to learn a line that can separate these 2 classes. How this line we draw? Here we can draw by looking at data, but in machine learning, so it will automatically, we can start from some random line, maybe like this side, or maybe this side or this side. And with the passage of training, start learning and come to the place where it perfectly divide to sets, so like this one. This is our in the process of learning, basically we are finding this line that separate the 2 sets. Okay, so the equation of line is very simple here. Weight into value x plus c, the y-intercept. So from this line, we can assume that c is 18 because it intercepts y-axis at 18, and then 2x means the value x-axis big 2 times than value on x-axis by looking into the here. So we can assume that 2x1 plus x2 minus 18 is equal to 0. So this is what we get from this line. But actually, these are the ways that model learn during the training process. How it will learn? Let's start. Here's a neuron. So we model that problem into a neuron. So neuron, there are 2 inputs. One is the test, other one is the grade. It come into the neuron, and here we have the equation. Equation is wx plus c, and then we get the output. So w is the weight of each neuron, each input. So if we are here, we have 2 inputs, we have 2 weight, w1 and w2. Then input is x1 and x2. And then the bias is the weight of this neuron, which where we call it is the intercept c, but here is the bias. So actually in learning, we need to find weight of each input and the weight of neuron itself. That's called bias. So these 3 parameters we will learn during the training process. So in this case, we assume that the first input 2 times, this is 1, and then the bias is 18. When you add all 3, we will find the equation is accept or reject. So it gives us a value. If a value is greater than 0, we accept. If value is less than 0, we reject. And we take that as step function. Step function is if value is greater than or equal to 0, it is accepted. If less than 0, it means rejected. Okay, so let's take example. The example here. So we have x-axis, x1 and x2. These are 2 input variables, and these are some data like training data. So we assume that it's our random lines, random. We select some random lines. Okay, and on top is the one that are accepted. On the bottom is the one that are rejected. The blue color in the blue background is mean these are the 2 positives. Mean the actual these words have accepted, and they are in this area. And this is the false positive, means this will actually reject, but somehow it comes here. So because this is the random line, we draw randomly initially. So because of that, we need to basically find where the line miss those cases. We need to find those cases, and then we need to take those cases and to adjust the line. How it will work? Okay, so this is the value of this line, W1, W2, and this is bias. Bias meaning basically intercept the y-axis, and these are the weights of x and y. So we take those 3, 4, and 10. These are 3 weights of this line, and then we take the first case. What is the coordinate value? This can be 3, 8 x-axis and 3 on y-axis, and then this is actually come in this category. This means it's separate. We take is 1. Okay, so and then if it's wrong, subtract it, and these are the new values of this line. And when we take these new values, we put in this equation to change line. But here, so we are taking the difference as it is. If you're taking the difference as it is, it means at every instance, it changed a lot in the line. So we don't want that. We want to learn small step, not a big jump. So I will tell you later why a small step. But so you can imagine that learning step by step with small step is easy and stable to learn a good thing. So to make a small steps, so we add a learning rate. Learning rate means so how much the distance, the difference is whole mean 1%, 100%, 1, or you take a small like 10% or 5%. If we take 10% means 0.1. To multiply this difference, the 0.1 to these values, and then add into the actual value like that. So now these are the new values of this line. When we enter these values into the line equation, line will be like this. It will try to come closer to this one. Basically, we want a line that separate the blue and red separately. So same, take the other example. This is the second point. We take this one that's misclassified. These are the coordinates for that. Here we have the instance which is come into the rejection, but actually this student is accepted. So we take the values addition, and then we add it into this equation. The new equation will be like this one, and then the line will become like this one. So if you repeat this process a number of times, we will find a line that will separate these two. Yes.
How do we decide the learning rate?
Okay, so learning rate is a heuristic. So it depends on the data. If you data and also depends on the model. At this point, we take small step, any small step. If you take too small, to take long time, might be to stuck some local minima. So if it's take too big, maybe it jump away. So it will not come into these associations. So intelligently, we take initially with high learning rate, and over the period of time, we're decreasing the learning rate so that it will converge to a better solution.
Bias for misclassified point is 1. Why?
Sorry?
The bias for misclassified point is 1. Why is 1?
So in our first example, I'm telling the only the cases that are misclassified one by one. So you can see that batch. You heard a term about batch size. Batch size means the amount of data that you will take at once to change the weights. Here we're taking 1 sample, means batch size is 1. If you take a 10 sample, we take the difference of 10 and take the average of those difference, and then you can adjust the weight. That means batch size 10. We take 10 examples. So here we take 1 example. This is a basic perceptron algorithm. So in perceptron, take 1 at a time because we have 1.
When you first use subtracted to get to the new,
And here we add.
why are we doing?
So okay. So because they are this one is the
False positive?
false positive, but the actual value is 0, but predicting as 1. In that case, we're taking a subtraction. Here, the actual value is 1, but predicted as 0. we take addition. I will explain in this next slide.
So does the sequence of the number that we are picking false positive and
Doesn't matter.
It doesn't matter.
Okay. So here, this is the kind of like a pseudocode algorithm. So start with any random weights. It can be any number, 0.5 or 1, maybe any uniform distribution of weights of all the inputs and the bytes. So if it's misclassified, so we have to, because this is binary classification. If prediction is 0, then for all the inputs, we add the weight with the difference of the value with the alpha is learning rate. If prediction is 1, then we subtract. So in this case, so we learn 4 things. First, step function, which is at the end. After the neuron output, we decide what will be the decision. If it's greater than 0, that's 1. If less than 0, that's the negative rejection. So we call step function. Second is the prediction function. Prediction is we multiply each input with the weight of that input, sum off with the bias of the neuron, that give us the output, the prediction. And we apply on the prediction the step function, and that give us a final value. And then when we take the difference of this one, that becomes error. So in case you ask why addition over there, subtraction over there, if actual value is 1 and you're predicting 0, difference is -1. If actual value is 1, you're taking difference 0, the difference will be 1. So for that reason, we take that negative and positive. And that's the error. We take the error with the learning rate multiply with the input, and we add the bias with that. So this is how we change. This is basic perceptron. Yes.
Can we go back? There is a prediction function. There is a theta before W1. What is that?
This is function. Function. This function is.
Function. Okay.
Okay. So let's go and run this code and see how it works. So there's a code called perceptron1 in the code directory. So very simple code. So we start with the first function, load data. This is just one file that have all those values, x1 and y1, and the prediction. So we're just loading from the file and returning x and y. And then, so this is prediction function. In prediction, we have weight, we have input, we have biases. So score is the output. So start with 0. And then we take all the input, multiply the input with the weights, and add in the score, and we add bias in the score. And if the value is greater than 0, that's custom function. We return 1. If value is less than 0, we return 0. Okay. So, and this is the training algorithm that train the perceptron. Perceptron mean one neuron. Okay. So we take all the inputs, and then we first predict, compare with the error, and then we take the difference error, and we change the weights, we change the bias, and we continue this process. So it will be changing the weights, learning. And then this is the, okay, so in deep learning, so we have terminology like epoch, and we have batch size, and then we have one example of one case. So one case is just one row or one values or one images that we want to learn, and then we take a number of images at once to learn that called batch size. And then we have a continuous loop of batches. After that, one thought is, if you have 100 images, and we take 10 batch size, and after 10, one batch, and then after 10 batches, we have 100 complete training. That's one epoch. But you can have like 100, more than 100 epoch, or more than 10 epoch. So it's up to you how you can define. Epoch means how many times one instance will be used for the training. So in one epoch, one instance minimum if you have like one. Same size.
Same set that is used multiple times?
Yes, we want same data we training multiple times. That have more than one epoch.
So you're changing the weights every time you train.
Yes.
That's what you're doing.
So because we are not, when you are changing the weights, initially I explained, so you have low learning rate. We're learning step by step. So we're not taking the whole difference and then adjust the weight. In small step, then basically against small step. Epoch. So we take this code. One is if you can install all the packages that required. If you don't install, you can start just run the code. When the error comes, just install that package at the same time. Let's do that. So first run this script, Python perceptron 1. So it's learn, and then it gives 52 accuracy. Okay. We can also run here. Okay. Until we find a line that is correctly classified, but still we have small errors.
I think you have a question. The error function should be continued and
Yes, I go there. Okay, so discrete means we have here the first example that I explained earlier. So the one that are incorrectly classified, take these two as discrete, and then we change weights here. But in continuous, so basically instead of taking the 1 or 0, we're taking the likelihood of probability, that what is the probability of this instance belongs to this class. If high probability, it means they are correctly classified. If low probability, it means they are incorrectly classified. So in this case, so we have two classes. So one class which is closest to 0, this means 1, and then there is a threshold in the middle, 0.5, and then the second class, which is ideally 1 but close to 1. So this is the case when we have discrete, we have step function. But in case of continuous, we use sigmoid function. And sigmoid basically give value between 0 and 1. There's not 1 and there's not 0. Okay. If you have, if you have binary classification, you can use sigmoid. But if you have multi-class classification, then you have a softmax function. That's the form of sigmoid for multi-class. So we use one hot encoding. One hot encoding is, so we have number of classes is the output. So the one that is the correct, the 1, all are 0. So you have multi-class. So see, if this is the correct, the 1 here, but all are 0. This is the correct, this one 1, all other are 0. It's a one hot encoding. Okay, so if yes.
For one hot, should we use k-1 for the encoding? Meaning if you have 3 classifications and one is 1. I thought there was something where if you know that 2 of the classes are not true, then by default the third one will be true.
No. So we want to have, like, for each class we need to find the probability, and we pick the one that has highest probability, and that will be because of softmax function. When you apply, so suppose this is our neurons, and the last layer of our network is the decision. So if you want to make it classify, that will classify 10 different type of objects. The last layer will have 10 neurons, and each neuron associated to one class. So when we give an image to the network, it goes into the network, and all 10 neurons, they have some values, and values is always from 0 to 1. And the neuron that has the highest value, to pick that neuron, and this neuron is the label of this neuron will be the label of that image. We are all other still have values, but those are lesser values. This means the model is had high probability for this class and the low probability for other class. Okay, so to cope that concept, we use one hot encoding. Means we pick one output that has highest probability. Okay, so if we have a 2 model, so we have their probabilities. So we want to, which one is better? How we decide? Okay, so for that, so maximum likelihood means probability is basically when we have input with weight and biases, and we give a prediction function, we get the output. So this is the output, and the output is like likelihood would belong to one class. When take the inverse, that this is the blue class. When take the inverse, that means this instance belong to the other class. So, okay. So here we can find for all values, what is the probability that these objects belong to blue class. So this one higher because it's already in blue class. This one lower because this is the red class it have low probability to belong to the blue class. And here is higher because this is the wrong prediction, but still in the blue class. And this one is lower. That's because this is a real object that belongs to red class, but this belongs to the blue class is low probability. So if you take this one is 0.7, that's the actual probability belongs to this class. And 0.3 is the opposite class. So if you add the real probability means this is the blue class, this is the blue class, and these are the red class. We take the probability in the red class and multiply all the probabilities, and that probability means this is the model, how much model stronger to predict the object. Higher the value, higher this value means the model is more stable or better model. Lower this values, the model have lower prediction values of power. So if you ask questions about two models, which one is better? What we do? We should compute the probability on the test set, and the model that will give highest probability is the best model as compared to other models. So if we have two different models, we take the probabilities, multiply them. Okay, so we multiply them. So here we have only 4 examples, and you know probability is always between 0 and 1. And if you have 4 examples, we have like 100 or 200 or 1000 examples. When you're adding all those fractions, the value will be very small, teeny. And it's very hard for the scientists to see the difference. Then when we have very small, very big values, then we can use the log. And we can use the log here, natural log here. When you apply log on small values, which is less than 1, it gives us negative values. When it's given negative values, so then the output become negative. So to make it positive, we take negative of log. When we take negative natural log, that gives positive value. And that gives us the cross anisotropy. So basically, when we are in machine learning, we want to have models which have highest probability or lowest cross anisotropy. That's our opposite. So our goal is to increase the maximum likely probability and decrease the cross anisotropy.
What is cross entropy?
Cross entropy is the negative of natural log of the output prediction. Okay, so the next concept is gradient descent. Gradient descent is so when we have initially weights, which is randomly initialized, and we input data to the model, and we get some prediction. Some are right, some are wrong because we have random weight, and so we have some errors, and we take that error, multiply with the learning rate, and we adjust the weights. So gradient descent is the algorithm. Basically, you change the weights step by step so that we are decreasing the loss, decreasing the cross anisotropy. So for that, so optimizer in deep learning, optimizer is basically the algorithm that change this weights, the process of weight. Here we have in previous perceptron, we have step function, but here we have sigmoid function to make it continuous with differentiable. And this is the same one, the predict function. Here, instead of taking the difference, now we're taking the negative of natural log. And that's the error. Now, this is called cross anisotropy. And when we have cross anisotropy, we take that loss function, multiply with the learning rate, and change the bias and weights. Bias and weights are the same. Like weights are the input, weight of the input, and bias is the weight of the neuron. Okay, now let's go to the program gradient underscore descent. means there's no pandas here. If you find that error here, when I run the code, import pandas as PD, there's no package pandas in here. So what you do, simple pip install pandas. Here's the code. Let's check into the code how it changed. Okay, the first is the same function, it's loading the data from the CSV file. Second is the this plotting. Third one is the display. So these are functions for the displaying, and this is a function for sigmoid function. So previously we used step function, and here we are using the sigmoid function. The difference between step function and sigmoid function is step give you a discrete input, either 0 or 1, and sigmoid give you a continuous output, a value between 0 and 1, not 0 or 1. Okay, that's basically probability of the model prediction for the class. And then this is error formula. So we're taking the output, actual, the ground truth is y, and prediction is output. We take the natural log, multiply the, that's the your error function, and this is the weight change. So basically we have the input, weight, and bias. We get the output, and we take this output difference and multiply with learning rate, and change the base and weights and return back. And this is our train function. Let's start from the here. So we start from some random seed. Number of loops, number of iteration is 100 times, and then we have learning rate 0.01. Let's start first from 1, then we change the learning rate, how it affect. This is the file name which have the data, and first you load the data, you draw all the points on the plot, and then you call train function. When you call train function here, so train array initially 0, empty, we didn't start, and then so feature is the input. We have two variables, x1 and y1. So then last num. So we initialize the weight with some normal distribution. So you can use either 0, either 1. I use the normal distribution. And bias is 0 because we have only one neuron, so 0. Okay, and then epoch means how many times you train your network with same data. Okay, for the first time initially weights are 0, all the weights are 0. Okay, then we take the weights and target. Weights means the features means x1, x2, and targets mean the y. We take all, first predict, find the error, change the updated weights, and that's the learning. When you've done the learning for one whole time, then you compute the loss for the after one epoch and display the line of that loss. Okay, let's run this code first. Yeah. Python gradient. So another package matplotlib. This is used for displaying the graph. Here, the conda is corrupted, so I need to see the path, but I can do it here directly. Let's run this code here. Okay. So start with this is initial line, random line. Start with that. These are the inputs, the blue and red one. Start this initial line, and then it goes somewhere here, and then start learning them, and it finds this last line, black line, that will change the learning. So now we can do a couple of things. First, I did run this experiment for 100 times, I mean 100 epochs. Let's do it for 5 epochs. Let's do 5 epochs. So because I'm drawing the line after each 5 epochs. So start from here and come to that line. Let's go by 20 epoch. 50. 20 small. slightly better. Okay, let's make learning rate change. I start with 0, 1, make it 0, 0, 1, means low learning rate. Now it's taking, see, oh, I need to start from again. So this is first line starting from here and come to this last. Okay, so now change the learning, it make high. So you have slow learning rate, but more epochs, more time training. So it's up to you how you can play with that. Sometimes so you have high learning rate with less number of epochs, and sometimes you have low learning rate with high number of epochs. It also depends on your network, and it also depends on your data. How, if there is noise in the data, then you have a low learning rate. Why? If there's noise in data, means the data is mislabeled, so it's wrong label. So if you take that data, when you take the wrong label in the network, means the model prediction is right, but the actual ground truth is wrong, and we're changing the weight for that. And that's like, if you have high learning rate and then the wrong prediction, and that high learning rate affect the model learning very seriously. So general perception is, if there is a noisy data set, then you go with low learning rate and more number of epochs, so that the effect of noise on outliers onto the learning is lower. Any question? Yes.
What are the green lines signifying?
So these are in between step. Starting with this one, these are in between step, and this is last.
What is that?
Sorry?
Black inside the yeah, yeah. What is that?
This is, I think, previous one. I didn't close this diagram.
Oh, okay.
Let's do it again. It's not here. This is the initial random, and then these are the intermediate, and this one is the last one. So you can play with that. So there's a lot. You have epoch learning rate. You can play with that. And you can also change the initial weights. So I start with normal, but you can start with either 0 or 1 or any other number. Okay. So in perceptron, so we're taking 1 at discrete, and here we're taking more than all the instances, either correctly or incorrectly classified, and we have like instead of discrete, we have continuous function. So in this file, there is a, so this is a code that I wrote, but there is a built-in function in the scikit-learn. Scikit-learn is a package from one of the community in Python. So we have all these functions available there. If you want to use, just don't want to code, just use their package, and they have function there. You can do the same thing. Okay, next is cross validation in machine learning. So the cross validation is normally used to assess the quality of the model. So in cross validations, if you have a 10,000 images and you want to test the model performance on those 10,000 images, but you need to divide some into training and some into test set. So if you initially, normally people, what they do, they take 80% as a training set and 20% as a test set. So they train on 80, they test on 20. And this selection, most of the time is random. And there's possibility that the 20% that is selected is easy one, a harder one, or mix of easier and harder. To address this issue, so they come a which called cross validation. This means if you have instead of taking only one-time experiment, you take 5 times. First take first 20% as test set and rest 80 as a training set. Next time you take another different 20% as a test set and rest 80 as a training set. And you repeat for 5 times, mean 20, 20, 25 times. You repeat the experiment for training on the rest of the 80%, and you have the average of all the results. Then you see the model performance. That's called cross validation. Okay, so that's the, we take this only one neuron with perceptron and one neuron with gradient descent with the. So how about if you take more than one neuron? That's called multi-layer perceptron. So you have neuron in more than one layer, in one layer more than one neuron. So here, this is one layer with 3 neurons. And you have more than one layer as well. So you can design your own network. So the input, because we have 2 inputs and 1 neuron, and then the output, right? So it's kind of like, we have 2 inputs, 1 processing unit and 1 output. That's a perceptron. So if you have like more than 10 inputs, all go into 1 neuron. So it means there's only 1 neuron that's learning, very restricted. So we can design the 10 inputs. We can say, okay, let's take 2 neurons, and all 10 here and all 10 here. Now we have 2 neurons, and the output of these 2 neurons merge into the 3rd neuron, and that's the output of the model. This means you have 2 layers, this first layer and the second layer. First layer, input is from the input, and the output go to second neuron, layer neuron, and the output of second layer neuron will be the output of the model. In this model, we have 2 layers, and first layer have 2 neurons, and second layer have 1 neuron. And in the people can design, you have as many neurons in one layer, you have as many layers of neuron as you want. So it depends on the problem. So what is the, how you decide it? So you decide based on the complexity. So if the data is, problem is very complex, it means there is more neurons. And each neuron learns maybe one part of the data problem. So if you have, if you are building a model to classify a face, so this is like person A or person B. If you want to classify faces, we all are human. We have all the have eyes, nose, lips, forehead, everything same, but there's slightly difference in that. To learn all these small minor details, you need as number of neurons in that. Maybe 1,000 or more than 1,000, maybe 100,000. Let's run the second program, which is gradient descent 2. Yes.
Where do you specify the number of neurons and number of layers in your program?
We didn't go there. We'll go later. So in previous programs, we had just only 1 neuron, 1 processing unit, 1 neuron who is learning things, and we have 3 weights: 2 input weights and 1 neuron weight, and that 3 weights decide based on the input what will be the prediction of the model, and we decide it's about 90% accurate in prediction. Okay, let's run the second other program, which is gradient underscore descent underscore 2. First, see what is in the code. So, I'm an MNIST. The data set publicly available, and that data set it has the digit 0 to 9, 10 digit, and those digits are handwritten. Those are like images. Size of the image is 28 by 28 pixels. Small image, and within the image there is a grayscale, not the color. Grayscale image value range from 0 to 255, and that give us a number. And the problem is how you can from the image what number is in the image. You need to predict. The input to the model is the image, which has some number, and the output, the model tells you what number is inside the image. And numbers are not like the computer generated, LED generated, it's handwritten. It can be very shaped. And those numbers they basically extract from the zip code. The zip code numbers that on US. This problem start from 30 years, 25 years ago, 30 years ago, and US mail, and they take the zip code. They want to digitize that. So from the camera, they want to recognize what zip code is in this written by hand. So they take the extract all the number from there. So all these data sets are available with the Keras. Keras is a kind of framework, and that's high level. Okay, let's start with. So we have maybe familiar with the Tensorflow, PyTorch, MXNet. So these are the deep learning framework which have all the packages for the how you can design the neuron, how many number of layers, what is the activation function, sigmoid, step function. There are other type of activation function like ReLU, and then there is different type of optimizer. We use simple, but they are more well as you ask. And initially we have high learning it, and over a period of time we have low learning it. All the optimizers are in this package. So that's kind of like whole framework which have all the functions that we need to build a deep learning model. So Google make the TensorFlow, Facebook make the PyTorch, and Microsoft make the MXNet, and then there's a Cafe, which is previous model, which is mostly replaced by the PyTorch nowadays. And then Keras is on top of the TensorFlow and Theano. Theano is another framework. They are high level language, which is make life easier for people who don't like a lot of code in TensorFlow. They make it in Keras. But nowadays, last year, Google they launched the Tensor 2.0, which have built-in Keras within that. So they're easier for us to program now. So in Keras, you see on top in Keras. So when you install Keras, like pip install Keras. So they already have a lot of databases in the package, in the framework. So you don't need to like download the database from here. Just include the database from the package. From Keras databases, datasets, import MNES. So it import all the data into the program. Okay. So the program is, so when you load data, it load all the images from the remote server to your program. So we have X train, Y train, X test, Y test. X is normally used for the inputs, the images, and Y is the output of the label. So X means the image, and Y means what is this image? 1 number, 2 number, 3 number, 0 number. And train and test, we have two sets. Trains used for the training and test used for the test. So 50,000 images in the train set and 10,000 in the test set. Okay. So when you these are the images, which is like grayscale images. The pixel of each location is 8-bit integer, unsigned integer. Mean values range from 0 to 55. So I convert it to float, so it have like more better for learning, but you can also use it as an integer. It doesn't matter. So I convert it to float, and then I take the width and size of the image, and after that, so this function NP utility to categorize, that's one hard encoding. Number like 0, 1, 2 to 9, which is a label of the image, it convert into a one hot encoding. Means if you have y underscore test, this means the test set image first. What is the label of that? It can be true. When it can be true, when you give this to this function, it will give you a C. Because we have 10 classes, we have 10 bits. This means 0, 1, 2. That will become 1. It's take input 2 and output will be this number. So that's the output of the. We convert into that because when the model predict, model return this number. Model return this number, and we need to compare with the actual. This one. So we need to compatible with the same output that the model return. If they are same, this means the right position. If they are wrong, it means wrong position. Okay, so yes.
So just to understand the input data, for example, you said the train has like 50,000 images, right? And then each one has.
Okay, let's do one by one. Let's run this code one line by line. Okay, so copy this one here. You don't have a Keras install. Let's install. Oh, let's change the environment. Where's the environment? Install from here. So install the Keras and TensorFlow. Okay, it takes a few seconds. When it's finished, then in the meanwhile, I will go to slides. Code slide. It will not go there. Okay, so I'll explain you. So we have images, 50,000 images in the training set and 10,000 in the test set. Each image size is 28 by 28 pixels, means 28 rows and 28 columns. Okay, and then I will output the shape of the X train, Y train, X test, and Y test. So you need to know what is the input and what is the output. Okay, so then I will create a deep model. So if you see that, so we have you can design your own network, but what I designed. Yeah. So the input is a image. What is size of the image? 28 by 28. Means we have 28 rows and 28 columns. So what we do, so we make it flattened. Means we take 1D, convert into 1D. All the columns become to the columns at the bottom of the first column. From 2D you become 1D, and that's the input to the model. So when you convert 28 by 28, it becomes 794 something like that. This is number of input. This is data. Now the network start from this input. Then we design how many neurons you want, 10, 20, 30, and how many layers you want. And the last layer should be the number of classes. How many classes we have? 10. So at last layer should be 10 neurons. And each neuron represents one digit.
Is it always that if I have more layers and more neurons, you get the right answer? It just takes more time, or is there,
Okay, so
is there some magic to that?
it's not like this way. So it depends on the problem. If you have too many neurons and you tell us formula is simple, data is very small, it will not run very good. So you only need, and second is take more training time. Take a lot of effort to train. So now it's a small problem. It takes few seconds or few minutes. Like I work on a problem like on facial recognition, it takes more than 10 days to train one model. If they're with a small network. When they increase in network size, take maybe 1 month. They have the network there that take more than 1 month. Okay. So you need to have a small network so that to learn in small time. And deeper network need more data limit.
So the deeper the network, the more data.
Because you have more nuance to learn. Okay, so install. Okay, Keras install. Okay, so let's see, it's install here. Tensorflow is here. Keras is here. Okay. Refresh this one. Let's see. Import Keras. Yes. Okay, copy. These are downloading data. Okay. So now we have X train, Y train, X test, and Y test. So if you want to see the shape, X underscore train dot shape, X capital. So we have 60,000, not 50. We have 60,000 example and 28 by 28 size of each image. Okay. After that, we just from the unsigned int we convert into floating point and normalize value from 0 to 1. Okay, and then this will give us the size of the image width and height 28 by 28 here. Okay, and the output. So Y train. Let's see what is Y train. 5 digit. Let's see X underscore first. So these are the values for 5. So you can display. Okay, it takes some more time. Maybe I would. You can Google it how you can display it, but for now we just move forward. Okay, so this is one to convert into 1 hot encoding. So now you can say Y train. So its fifth position is 1. 0, 1, 2, 3, 4, 5, and that's all 0. So you convert 5 digit into 1 hot encoding. Okay, and then so this tells number of classes in the network. Number of classes. And okay, so this is a network designing. So right now we are building a sequential network. Means we are layer by layer. The first layer, second layer, third layer, fourth layer. We call sequential network. The model is equal to sequential. Sequential is the used for making a sequential network. So then first layer. What is input to the first layer? The image. And image is 28 by 28. We say that this is image size. Input I make it flattened from 2D to 1D. Okay, this is first layer. That is input layer. Okay, and second is the 10 neurons. That's it. So number of classes 10. Model that add. So when you say model that add means it add 1 layer. The first layer is input layer, and second layer is number of neurons, the 10 neurons. And then activation is softmax. If you use binary classifier, we use sigmoid. When the multi-class classifier, we use softmax. And then the turn initialization 0. So what will be the weights when you start the model? We make it all make 0. Okay, but there are other ways to initialize some distribution. Okay, so these are 2 layers. First input layer. This is last output layer. Okay, then this one is the how you train your network. So compute the cost entropy. If it's binary function, we use the binary cost entropy. If it is multi-class function, we use categorical cost entropy. Okay. And then optimizer use Adam. So there are bunch of 7, 8 optimizer. So this optimizer have the facility, it's higher, and then you can change and get later. Okay, Adam. And which metrics you use to evaluate accuracy? Accuracy means true prediction divided by total number of prediction. Make sense? Okay. So this is for the to training. Yes.
Why did you use sequential model? Why did you decide to use sequential model in this case?
So it's first basic model, simple model from here. We are going to convolution network. We take it as it is. That's the next level. Complexity. But this one is taking this layer by layer. Okay, done. And then so this is the one model checkpoint. Save the model with name model.h5 and monitor validation accuracy. So there are two accuracies: accuracy on the test set and accuracy on the training set. When you say that accuracy simple act, it means the training accuracy, and when you say the val_ accuracy, it means the test set accuracy. And verbose means you want to, when training happening, you want to display all the output from the training process in the middle. Save best only. So when you're training, you want to save all the models of each epoch, or you want to save only one model that's the best during training.
How do you decide on the optimizer?
So optimizer. So at this point, there are two very famous optimizer. One is the SGD and other one is Adam. Both have different way. SGD is more like the one that we used previously. So change in slow learning rate, but long epoch. And there is no change in the learning rate. We can write a small function after 10 or after 20 epoch, decrease the learning rate by 10% or 20%. Or you can write also a script that when the loss is not changing a lot, then it decreases the learning rate. So you can write separate script. But in Adam, they have built in inside, they have momentum and other terminology, which basically change the learning rate and make the model learn very quicker. So over the period of time, you learn which optimizer work depending on the model that you design, and depending on the data that you have. Okay, so okay, mode means, so which one you take? We are considering the accuracy here. This one, monitoring accuracy, so means the highest accuracy maximum. If you're looking for loss, then you go for select minimum, because loss should be minimum, accuracy should be maximum. Loss is the difference between the prediction and the ground truth. That's the loss, should be minimum, so that we have better model. And after that, this line start training. So input is X train, and this is the output, the ground truth for this X train. So epoch 10 size 200. That means previously we take one instance, do prediction, compute loss, change the weights after one. Now we take 20 images at the same time, compute loss for 20, take the average, and then take that loss, average loss, and change the weights now. If there's one outlier or noisy, then we have the effect of that outlier when you take average is minimized. So this is another recommendation. When you have a noisy data, take high batch size, so that there's some outliers in the data. The effect of outlier will be minimized. If you have low batch size, if one is outlier, the effect of that outlier to training is bad. And then validation set is test set, and then callback. We put this checkpoint callback, means when training is finished, what we do? So we take save the model, which is the best one based on the val accuracy. Okay, and then this one is to evaluate the model on test set and run the result. Okay, so let's create line by line. Okay, so okay, let's see model dot summary. So we have two layers. First is pattern layer, second is dense layer, number of neurons. So this is the batch size. Norm means we didn't design the batch size later. We don't know what is batch size, but we know the input 784, which is the 28 multiplied by 28 pixel. And then second is dense layer, the output layer, number of neurons 10, because we have number of 10. And then this is number of parameters. You just multiply these two plus add the 10 neuron biases. This will be the number of parameters, number of weights. Parameters and weights are the same. Okay, parameters and weights, they are same. Okay, and then these are the number of parameters to learn. Checkpoint. And then start training model. So it's training, 20 batches. Then if you see accuracy increasing, loss is decreasing. So we have 10 epochs, 10 times 1, and it starts with if you can go up.
You're determining the parameters.
The parameters determine number of neurons, the input is weights, and then the number of neurons is biases. You can add this two, you can know that number of how many parameters there. So we have like 28 into 28 image size. So when you make it 1D, 28 by 28 becomes 784. And then we have 10 neurons. This means 784 multiplied by 10 means 7,840. And then we have 10 neurons, the 10 biases at 10 becomes 7,850.
So only because it's MS database, the data set that you're getting such high accuracy with just a single layer.
Yes.
Linear perceptron, right?
Yes, it's simple data set. Okay. So what accuracy is 92%?
Using any CNN or
yeah, we have. I will go data on that.
What I'm saying is, if this were some other images, then you would attain 90%.
I know. Yeah. So this is a problem start in 90s, and at that time we don't have like a step over. So at that time, the accuracy is 70, 80%. But over the period of time, we learn. Now we have accuracy 99.99 something on our latest models. Okay.
Is the number of neurons equal to number of classes?
The output layer. If you see the network design, what we design, we have just two layers. First, the input layer. Input layer size is equal to the input size, and the output layer size is equal to output. We don't have an intermediate layer. Let's add one more layer. Okay. Okay. So this is the, let's run this prediction and see what is the results, final result. Okay. So now what we do, we can add one more layer here. So model dot add. Let me see if I already have something. No, let's do it here. Model.add and dense. Dense is means one layer of neuron. So how many neuron you want? So let's take 100. And then activation. This means after the output, should you take as it is or you apply some activation? So normally the last layer is the result. So we want either sigmoid or the softmax that give us the prediction. But intermediate, the activation function means the output of neurons you take as it is or you want to modify the output. So over the period of time, we learn that ReLU is the better, and ReLU is basically ignore all the negative, only the move the positive. If you input to the output of the model, it is predicting anything that is from negative infinity to positive infinity. And you see that pass all the value which is greater than 1 and remove the value which is less than 1. So means move all the positive values. So basically, we are learning anything that is positive and we are removing things that are negative. Means each neuron learn the positive values, not the negative values. That's called ReLU function. So for this one, so we say that equal to ReLU. That's it. Okay. So now run again.
Okay. Like a why ReLU works, is there some intuition behind this?
So I will give explanation later. There is one slide for that. Okay. And let's start this one. One here. Okay. Model dot summary. Now, how many layers? We have 3 layers. First input 784. Second 100 nuance. Third 10 nuance, which is 10 class labels, right? Now we have so 784 multiplied by 100 and then multiplied by 100 biases. That is the number of weights here. And then this new one, this multiplied by 10, this multiplied by this, that will become number of weights here. Make sense? So we have 784 inputs. So those are nuance 784. Each nuance have one in, and then each nuance have its own bias multiplied by. Okay, this is first layer, and then second layer is 100 nuance. So these 784 come all each nuance, so means multiply by 100, and each nuance have its own bias. Add 100. That's the number of weights for this neuron, for this layer. Number of weights in this layer. And in next layer, we have 10 neurons. And input to this 10 ones 100 neurons. Mean 100 multiplied by 10 become 1000. And 10 neurons basis of add 10. That's the number of weights in this layer. And when we add these two, that's total number of weights in this model have. It's clear to everyone? Any confusion? Okay, good. So we add the checkpoint and then we start training. Now, this is not taking more time. See, last time it's very fast because we have less neurons. Now we have more neurons, taking it very slow. Add more layer, we get it slow and slower. Now, I supposed to jump from 92 to 97. The accuracy now is 97.14. When you run the validation set, so 97.09. Any confusion here? Okay, and the other concept that's I will stop after that because it's too much for one day to digest. Dropout. So dropout basically introduced 4-5 years ago. You randomly turn off some of the neurons. Why? So sometime when you're learning, if you learn too much, that's the overfitting, and you want to avoid that overfitting because you are learning again and again on the same data in number of epochs. Here's 100 or 10 epochs. If you are too much learning on same data, maybe some neurons overtrained. And to avoid that overtraining, we use dropout. Dropout basically is like 0.1 means randomly turn off 10% of neuron in the network. Turn off means their output doesn't matter. They consider 0. Okay, let's add dropout here.
Is it randomized, like kind of
Yes.
first and then?
Yeah. Okay. Everything is same in this code. So only two things is, so this is first layer. Then I add 400 neurons. Then I add dropout 0.4. Means 40% of neuron in this layer is off in this layer.
to detect the dead neurons.
Yes, that's an advanced concept. So not for today. Okay, and second is the 200 neurons. Okay, second layer, and then again drop by 20%, mean randomly turn up 20% of the neuron, and then last layer is the class label. The number of classes 10. Everything's same. You can okay. Let's use as it is the Adam, but I will change to the SGD, the other one. Okay, later. First run as it is. Dropout. I need to include dropout and dropout. Tensorboard. Okay, Tensorboard is a tool that we use so that when it's training ongoing, we want to see the graph, how loss is decreasing and increasing. So we can add that. So maybe next workshop, I will give a tutorial how we can add so that we can track. So we can see each neuron values, how changing, the weights is changing. With Tensorboard, it's basically a debugging tool. You can look all the layers of the neurons, how their weights are changing, how overall loss is changing, how the accuracy is improving. You can see during the training process, here training takes few seconds or few minutes. But when training takes more than 10 or 20 hours or 2-3 days, you track. I'll show you an example of that. Just a hold. Okay, now it's training. Now we have 2 layers, additional input layer, 2 hidden layer, and then 1 output layer, 4 layers. So it's taking further slower, taking more time. We introduce the dropout also. In the meanwhile, I can open that one. How it real training happening. Oh, so anyone have a charger? This is Tensorboard. By see, you can see start from here. The loss, the accuracy over the number of the clocks is the 120K. Not the other one. Anyone have this charger? Otherwise, my 5%.
USB-C.
Huh? The small, small.
Thank you so much.
Okay, so stop here, and then you can run the prediction. You can save all as well, 98.25. So by adding the more layers and adding dropouts, accuracy jump from 92 to 97 and now 98. So you can, yes.
The last piece, did you fine tune for retrain models?
There's no pre-train here.
I know.
We train from scratch.
I'm referring to your hand list. So did you increase your accuracy when you use pre-trained models?
Yes.
You did.
Yes.
And which one was it?
It depends on the data problem. Nowadays, by default, there's an image net, which is by big data set, but it depends on what problem you're solving. Like
for this problem,
for this problem, we don't need it. We already hit 98%. Why do you need for that?
okay, so because you fine-tune the famous publicly available deep learning models for handwritten dish classification. That's what I said.
Yeah, available, but if you're working on some harder problem, then you can go for that. Okay, so this is the so there are multiple matrices. This is one accuracy, one test set. This is another test set, and this is another test set. This is the for the face detection problem. The giving a face to define who is that face part.
What are the axes here?
Hmm?
What are the 2 axes?
So on the x-axis, the number of epochs. On the y-axis, the accuracy of the model. So you consider 120K number of time training. You can starting from okay, sure. Starting from 50% to 98, 95, 97% accuracy. Okay, so this is the experiment I'm running from today to work. Okay. Okay, so next go to slides. Here. So what we learned. So we know what is X-train. Type is unsigned integer. We convert it to float. What is flatten do is basically convert 2D to 1D.
X-train is a list or is it a NumPy array?
Which one?
X-train.
X-train is the name of the variable. Is when we have data amongst we download, it's like an 2D NumPy array. Okay, and the actual type of the NumPy array is the unsigned integer. We convert to float, and then we do flatten, make from 2D to 1D, and then softmax is used at for the class 1 hop encoding. Cross entropy, categorical cross entropy is used for loss to compute loss value. And then we use Adam is optimizer. And then I can run the experiment with STD. So this same, everything's same. Instead of Adam, we choose STD. And then we run this experiment. So you can also save your model by just JSON file. You can save as the H5 file or another file format. You can load the same model. And you can save weight and model separately. You can save together. You can read or load separately or load together. So it's clear. You can also like change the batch size and increase epoch. You can play with that. How this changing the epoch and batch size of our work. Yeah. So if you change, from Adam to STD, the accuracy is 92% because it takes long training time. Adam is quickly learning. Initially, take high learning rate, then it's quickly decrease learning rate. Yes. What's your question?
So based on your experience, is there any
Okay, this is one of the tricky questions. So it really depends on the problem. If the problem is very hard, you need more data. If the problem is very simple, like you want to classify dog versus human, maybe few unlimited enough. And you have pre-trained model, that also works. In some cases, like I'm working on some medical data, and medical data is totally different than the real data. Medical means cells, the body cells, maybe MRI, a CT scan, which is grayscale images. There is no like human, dogs, animals, buildings, cars, vehicles. So most of the 3D network are on ImageNet, which is real images from the camera, from the real, indoor, outdoor, human, pedestrian, animals. So even though when you have that big data set of ImageNet, we train network on that and then take that model, apply on MRI, CT scan, mammography, still perform better than from scratch. Because model learn something. So I will go maybe in today's time or just give you 5-6 minutes overview about how it's learning in case of. So these are the multi-layer perceptron because we have multiple layers. There's no convolution here. These are sigmoid function. 10H is another activation function. Reloop that I use linear as it is, and then leaky reloop means the value that are negative change less, the value that are positive as it is. And then these are lists of the loss functions that we can use. So use the binary, in case of binary classification, we use multi-class for category class entrophies, but there are other loss functions. These are the optimizers. These are optimizers available. Okay, so then we, for accuracy, we have matrices for accuracy and the mean absolute error. So you can play, there's a code over there, you can download the code, you can play with and learn things from there. And this is dropout, turn off randomly some of the neurons. Okay, okay. In convolution, so I just give you a small idea about the convolution. Convolution means you have small kernel. Kernel means windows, a small window. The size can be 3 by 3 to 5 by 5, 7 by 7, or any size. Should be the odd. And we take this kernel, and their kernel means they are, if we take the 5 by 5, the 5 by 5 matrix is some number 0, 1, 0, 1, some pattern, and we multiply on the actual image on first 5 by 5 pixels, multiply it, and you get one value, and that value is the value of the middle one. And then slide this kernel to the next, and next, and next, and next. And the same can generate the same. If you have like 3 by 3 kernel, then the first first column, first row, last column, and last row will be not come here because we're taking the 3 by 3 and compute value for this one. Then we have missing this one. Then we can, if you want to have same size, you can pad the last with 0, 0. Then we can get the last same size output. So why are we using convolution? If you have a kernel size, suppose I'm taking example of an image. The kernel is 0, 0, 0, 1, 1, 1, 0, 0, 0. This is kernel. When you multiply this kernel on the image, basically the middle layer line, basically it's finding the horizontal line in the edges, horizontal edges. If you're taking the kernel size like this one, that's vertical. It finds the vertical lines in the image. I'll show you example. This is a dog image. When you apply, you can see here, when you apply the horizontal kernel on your face, when there's a change in pixel value horizontally, you find the lines here, like nose, ears, maybe these areas. When you find vertical kernels, it finds like this line, lip line. See, the two different patterns. One is horizontal kernel and one is vertical kernel. The eye line is vertical, it finds this horizontal, it finds like this here.
Is that reverse? Horizontal is finding vertical and vertical is finding horizontal.
Yeah.
But is that
No. That's a mistake. So there's just two kernels. So you can imagine this is vertical and the diagonal. So basically in convolution network, if you are making a model that classifies face, what you need to do at first layer, maybe to learn all the different horizontal and vertical or diagonal edges. And then from those vertical, diagonal, and horizontal edges, you make shapes like curves. And that's the second layer of convolutions. The third layer of convolution, from those edges, they try to learn the shapes like eyes, nose, lips. And from next layer of convolutions, from those shapes, they're trying to learn objects. From two eyes, nose, it becomes face. So this is the way how deep learning works. So you have each layer learning one level of information. The layer that is closer to input, they're learning at basic level information. The layer that are closer to the output, they're learning at advanced level of function, advanced level of objects and information. So if you are if you are making a model that classify dog versus a human, there's a lot of difference between that. Maybe you need 5-6 layers of neurons, a convolution. But if you have a classifier that classifies male versus female, or young versus old, or maybe more for same person with different age, like when you are small, when you are bigger, but you have same feature. The more complex, more layer you know want, because more deeper you need to go into the image. If I give you an image of a dog versus human, with few milliseconds, you just see that. If you see two same dogs but different breeds, you go deeper. Look in the eye, look in the nose, think, oh, this is this breed and this is this breed. Means no, you need more detailed level of information. And then more number of neurons, more number of kernels, so that we have more number of information we extract from it. I will stop here. So if you have any questions, you can ask. You can. So maybe for next sessions, then we go deeper into the what are the different state of the art. So this is the input from here. So when you apply convolution here, we learn this one. When you apply the ReLU, remove all the negative values. This is without ReLU, and this is with ReLU. You have all negative values off. So then there are others of max pooling. So these are first model that one. And then LayNet architecture 1994 for the MNIST dataset. And this is the how it learned. Then so this is the one that GoogleNet. I use this model. In 2016, I used this model GoogleNet to beat pathologists in diagnosing the breast cancer, and we have better accuracy than the pathologists. And this is contest happened in 2016 in Holland, from all over the world, and we won this contest with 99.96% accuracy, and human is 96% accuracy, and our accuracy is 99.96 with this network. Yeah. So yeah. Okay. Any question? Okay. Good. Okay. Thank you.